projection. And this is a way of taking your three-dimensional environment and producing a representation of it in 2 dimensions on the projection plane, which is an image that you could draw on the screen, and that is a reasonable approximation, or a reasonable model of how we actually perceive the world with our eyes. And it's the basic kind of projection that we use to produce realistic-looking views of our 3-dimensional environments on the computer screen. Now, we're going to just show how. So there's one thing. It's one thing to be able to carry out the perspective projection. So take the 3D information and find out the locations on the screen, on the projection plane. Another aspect of it is using the perspective projection to solve problems or to draw out features of the projection. Now, the first thing is vanishing points. Now, I hope you're all familiar with vanishing points. In the perspective projection, lines that are parallel in the real world, they aren't necessarily parallel in the perspective projection. If you've got lines that run exactly parallel to the projection plane, lines in the real world that are exactly parallel to the projection plane, in their perspective projections, they again will be parallel. But that's special behavior. Most lines aren't parallel to the projection plane. And in the perspective projection, they will not be parallel. Now, of course, you're all familiar with this. I mean, these two, you see these lines here on the wood paneling? Okay, we'll assume they're parallel. They're both exactly horizontal, parallel to the ground. They're parallel. When I stand here and look along the wall, that's not how my mind perceives them. I perceive them getting closer together. And if the wall continued on a few hundred meters up Oxford Road, that's the direction I'm facing, I don't know, these two lines, if I could see them, they'd be getting closer and closer and closer. And eventually they would look as if they were meeting. So that's called a vanishing point. Okay? Or indeed, if you stand in the middle of Oxford Road looking up the road, the two sides of the road in the distance, as you look, the two sides of the road seem to be getting closer and closer. Or you stand on railway tracks. Of course, I don't encourage that, but if you do, you look into the distance. If the ground is flat, you'll see them getting closer and closer, and eventually they'll meet. So this is the idea of vanishing points. So it's illustrated here in this diagram. So in this diagram, these two top edges on the cube and this bottom edge, if this is a cube we're looking at, we'll assume it's a cube, then these edges are all parallel to each other in the real world. Okay? They're not parallel on the page. Okay? And if you carry these lines, the lines represented by those edges on the page, you carry them out long enough, they appear to meet at that point V2. And indeed, any line in the real environment which is parallel to those three edges, that line under the perspective projection will also go through that point V2. Okay, so V2 is called the vanishing point for those lines. So every direction in the real world will have its vanishing point in the perspective projection, as long as that direction is not parallel to the plane. Okay. If we were looking face on, straight on to the cube, so like when I'm looking straight onto the table, the front edge and the back edge of the table are parallel to my viewing plane. Okay, my viewing plane is the plane of the back of my eye. Those two lines are parallel. Those lines appear to be parallel to me. They aren't getting closer and closer. Whereas the two side edges, like even just here, standing looking at the table, the two side edges, even though I know they're parallel, they don't seem to be parallel. They seem to be kind of going at an angle. So as long as the direction is not parallel to the projection plane, any line in the real world parallel to that direction, all those lines will intersect at a vanishing point. Okay? So our problem really is just to try and extract this from our vector model of perspective projection. So this exercise 7.3, show how to determine the location of a vanishing point in the projection space, in the projected space. That is, where is the vanishing point for a family of lines parallel to a given direction vector h in the real world space, in the world space. Okay. So we'll switch to the screen now. We'll have a go at answering this, or showing the analysis of this. So it's a fairly general description of the problem. Just want a general analysis of it. So exercise 7.3. So h is a direction vector. In the world space, the real world, so to speak. And we'll assume it's not parallel to the projection plane. So that means with z coordinate non-zero. So we'll say h is hx, hy, and hz. Now we'll just deal in three-dimensional coordinates. We won't deal in homogeneous coordinates. The homogeneous coordinates, remember, are there in the implementation. We want to implement everything with matrices, including translations. That's kind of why we use the homogeneous coordinates in the implementation. We're just doing a bit of vector analysis of the problem. We don't need to use homogeneous coordinates. We can just stick with our three components for vectors in the real world. Sorry, I'm changing the way I write my z's here. Sorry. Just do that. So this is a direction vector with non-zero z coordinates. So any line in the world space, parallel to h has an equation, and as we all remember what the vector equation of a line is, an equation for the position vector of any point along the line. So h is the direction vector, p is a position vector of a reference point on the line. So this line is going through the point p, and lambda is our parameter. So lambda is 0, you're at the reference point on the line. And as you vary lambda, you start at the reference point and you move in the direction h, positive lambda, or in the exact opposite direction to h, still in the same direction, just out the other way, if lambda is negative. Okay. So that's what a general line in the world space is. And for p, we'll give p coordinates, use the same convention, px, py, pz. So p can be anything, it's just a reference point to the line. Now, the projection of R will be, we'll call that R prime. And this will have coordinates, so R prime will have coordinates R prime x, R prime y, and we won't say R prime z because it's in the perspective projection, so it's being projected to the projection plane, so it'll have z coordinate f, where f is the location along the z-axis where the projection plane is. So sticking with the setup of the perspective projection that we had previously. Then we know what Rx and Ry are. Rx prime and Ry prime are. Because, so in terms of individual components, what is Rx prime? Well, we know how the perspective projection works. Rx prime, remember, is just expression x coordinate divided by z coordinate times f. Okay, the same perspective projection coordinates we derived in the previous step. So for this r, this is going to look like f times, now the x coordinate of r is going to be px plus lambda hx. The z coordinate of r is going to be pz plus lambda hz. Which would be. And similarly, ry prime, similar expression but with the y components on the top. And still with the z components on the bottom. Sorry, I keep changing the way I write my z, sorry. Let's just stick to it here. So these are the components, the x and y components of the projected vector. But we still have the parameter lambda. Lambda is measuring how far along, is the parameter that sends you up and down the line in the reference point P. These are the x and y coordinates of the projection. Now, okay, what do we want to do with this? We want to figure out the vanishing point. If you look back in the picture, where is the vanishing point? Well, you get to the vanishing point by just traveling out along the line in one direction out along the line. Okay. So we want to take the limit of these expressions, take the limit of these. What kind of limit? Well, as lambda goes to infinity. Okay. Lambda is what sends you forward and back along the line. So we want to let lambda go to infinity. So we want to move in the direction h as far as we can go. In the real world, we'll be traveling along the line. And there is no limit in the real world. If you're traveling along the line, you just keep traveling along the line. You don't approach any limits, you just keep traveling along the line. But in the perspective projection, these two lines here, as in the real world, you just keep traveling along this border between these wooden panels. But in my perception of the world, in my perspective projection perception, as you travel along that line, you get closer and closer to this midpoint, where the point where my finger is pointing at. If I could extend this line all the way, I'd see that line just get closer and closer to that point. So that's the vanishing point we want to capture. So where is it? It's okay. We know it's on the projection plane. We know it's got z coordinate f. So what are its x and y coordinates? What we want to do is take the limit as lambda goes to infinity of rx prime. So the limit as lambda goes to infinity of this ratio here, px plus lambda times h of x divided by pz plus lambda times hx. So you need to remember back to maths fundamentals. How did we take the limit of this thing? Remember quotient rule there? Good. So you want to apply the quotient rule. Say the limit of this quotient is the limit of the top part divided by the limit of the second part. Except you can't do that. Because the limit of the top part does not exist. The limit of px plus lambda hx, well, px and hx are constants. As lambda goes to infinity, the top part just goes to as does the bottom part, or maybe minus infinity if hx is positive. So at the moment, the numerator and denominator do not tempt their own limits. So remember, the way we handled that was to divide above and below by lambda. So now this is px over lambda plus h of x, all divided by pz over lambda plus h of z. I'm not changing, well, I'm changing the way the fraction is represented, but I'm not changing the quantity. I'm just dividing above and below by lambda. That's okay. Lambda is certainly not 0, so I'm sending it off to infinity, so we can assume it's not 0. So I can divide by it. And now I can use the quotient rule, because now the numerator and denominator do have limits. Px over lambda, as lambda goes to infinity, px is a constant, so that's 0. Similarly, pz over lambda goes to 0. So this does have a limit, and it has the limit hx over h of z. since px over lambda and py over lambda, both of these go to 0 as lambda goes to 0. I mean, there might be 0 to begin with, if px or py are 0. Even if they're not 0, they're going to converge to 0 as lambda goes to 0. So this, what's this? Hx over hz. This is the limit of our x prime. So this is the x coordinate of the vanishing point for lines parallel to this direction. So the vanishing point for these lines, so why do I say these lines? These were lines parallel to this direction vector h. So this has x coordinates hx over z. Of course, the pleasing thing about this is there's no p's in here. It's independent of p. Now, p was the reference point on the line. So these two lines here between the wood panels, they've got the same direction. They're both heading in exactly the same direction, they're parallel, but they've got different reference point p's. But the vanishing point doesn't contain any p's. The vanishing point only depends on the direction vector. And that's kind of what says that in the perspective projection, these two lines are both converging towards the same point in the projection. Okay? They're converging to the point with x coordinate hx over z. There's no surprise what the y coordinate of the vanishing point will be. There's only one answer, but it could be. I mean, hy over z. By symmetry. Similarly, ry prime, sorry, the limit as lambda goes to infinity of ry prime is going to be hy over hz. Again, so it's just exactly the same limit argument. Again, you see independence from p. The vanishing point is exactly, vanishing point here is say called vector v. Vanishing point v is hx over z, hy over z, over hz, and f. It's a point on the projection plane. These are the coordinates of the Now there will be you can also see from this that the vanishing point is different for every different direction. And that's maybe you have to check that a little bit. I mean, how could two different h's produce the same v? Could two different h's produce the same v? Well, in order to produce the same v, your two direction vectors h, this ratio, the ratio of hx to z, would have to be the same as this ratio. And the ratio of hy to hz in your new h would have to be the same as this ratio. And they both, yeah. But what are you saying there? If you're talking about two vectors in 3 dimensions, and they both have the same ratio for their x to z coordinate, and they both have the same ratio for their y to z coordinate, they are actually two vectors going in the same direction, but just with different magnitudes. So you can have different vectors giving the same vanishing point, but they'll be vectors pointing in the same direction. So in effect, you can say every different direction has a different vanishing point. Okay. So, is that okay? Questions? Of course, another point you can see from this, also notice the need for the hz not equal to 0 condition. This wouldn't make sense if we had h of z equals 0, because I couldn't speak of something over 0. those points, those directions don't have vanishing points under this perspective projection. Okay, when I'm looking at the table, the front and back edges of the table, they still seem parallel in my perception. Now, of course, if I look down that, if the table was long and I look down that way, yeah, then I'd see them start to converge. But then I've changed my viewing direction, and the front and back edges would no longer be parallel to my viewing plane, my projection plane, once I twist my head. But when I'm looking straight orthogonally against the front and back edges, those front and back edges are parallel to my projection plane, so I perceive the lines as being parallel. But I don't even at this short table, I don't perceive those side edges as being parallel. They seem to be heading towards each other. So it all ties together nicely. Any questions? That's a nice thing we can see happening with the perspective projection. The other problem is that of back projection. There's a bit of a setup of it here, and this kind of relates to stuff going on in games as well. So what's back projection? Well, if you think of one of these typical 3D person-to-person viewpoint games, you're controlling the game, you're controlling your character in the game, your character is moving through the three-dimensional environment. Wherever your character looks on the screen, you see the perspective projection of the environment. Now, if you want to interact with your environment, using the controller, or using your mouse or whatever, you point, well, okay, in your imagination playing the game, you might reach out and grab an object, or punch an opponent, or press some lever on the wall in the game. You interact with the environment of the game, but of course, what you're actually doing is manipulating you're either moving the mouse cursor around the screen and clicking, or using the joystick, you're moving some selector around the screen and clicking. So you aren't actually interacting directly with the three-dimensional environment. What you're doing is just selecting something on the projection plane. So what back projection is, the back projection problem is, if this is the view of the game at the moment, and I want to select something on this top edge, so I might select this point here on the screen. How can we take the information from the projection plane? But by clicking with the mouse, I'd select a point on the screen, on the projection plane. How can we project that back into the environment and work out which location in the three-dimensional environment I actually touched or selected at that point? So it's kind of the reverse. That's what's called back projection. Perspective projection is bringing the three-dimensional environment onto the projection plane. Back projection is selecting something on the projection plane and working out, well, what location in the real world did I select? Now, of course, there is no unique solution to this problem. Okay, there's no unique solution to this problem because if I move my mouse on the screen and select this corner point here, that corner point is representing every point in the real environment along this projector line. Okay? So who's to say I could have been selecting any point along this projector line? There's an infinite number of solutions. There's an infinite number of points in the real world that you could back project any point in the projection plane to. So the problem, as we've stated, it doesn't have a unique solution. However, if you give it some more information, then you can solve it. So here's a one simple case of that. So this simple case is that there's a line in the real world, So we've got 2 points, P1 and P2, in the world space. P1 prime and P2 prime is how they appear on the projection plane. And you can see the projected version of that line joining P1 and P2. So let's say I select this point on the screen with a mouse click. So the computer knows I've selected this point here, so I must have been trying to select some point in the environment that lies somewhere along this projector line, somewhere along this line. But we also tell it, well, I'm also selecting the point on the line between those 2 points, P1 and P2. Well, that extra bit of information should allow the computer to uniquely pick out this point in the real world, which lies along the line joining P1 and P2. So if we give it the extra information that, as well as choosing this point in the projection plane, I was also choosing a point on the line between P1 prime and P2 prime on the screen, but they represent P1 and P2 in the real world. Then we would hope, how can we calculate the coordinates of this point? Okay, so that's one instance of the back projection. So given this point on the projection screen, on the projection plane, how can we find this point on the line in the real world? Okay. So that's the problem we're going to look at now, 7.4. So let's look at the setup. Suppose that a point, well, it's basically the setup of that diagram. Suppose a point is given along the projected line joining points P1 prime and P2 prime. Show how to determine the point in the world space lying on the line joining the points P1 and P2 that is projected to a given point. Okay. So, well, if we want to deal with the perspective projection, the perspective projection is kind of defined on the component level. So I want to get the components of P1 and P2. So we'll let P1 and P2 be, so P1, how do I write this? Yeah. P1 is X1, Y1, Z1. P2 is X2, Y2, Z2. Okay, so these are the coordinates of my 2 points P1. So I've got X, Y, and Z coordinates indexed by 1 and 2. So that implies then that P1 prime should be represented as Fx1 over Z1, Fx2 over Z2, no, sorry, Y1, sorry, over, I'm going to write that again because it's too messy. P1 prime is Fx1 over Z1, Fy1 over Z1, and it's that third coordinate F, so it's on the projection plane. And P2 prime is a similar thing, just indexed 2. So Fx2 over Z2, Fy2 over Z2, and then again has Z coordinate F. So the line in the world space, is R equals P1 plus mu P2 minus P1. That's the vector equation for the line joining P1 and P2. It's got a parameter mu. So mu is the parameter that moves you from P1 towards P2. You vary mu from 0 to 1. And the projected line has equation. The line on the projected plane has equation, let's call it R prime, which is P1 prime. We use a different parameter alpha times P2 prime minus P1. So this is the line joining points P1 prime and P2 prime. This is a line on the projection. And so this back projection problem, so the problem now is basically boils down to, given alpha, find u. Okay. So by selecting a point on the screen, we'll think of that as providing the value of the parameter lambda. Okay. Lambda is the parameter on the line on the projected line. The line on the screen. So interacting with the computer provides the value of lambda, the point selected on the screen. We want to back project that. We want to find the corresponding value of the parameter mu, which gives you the point on the line in the real world that has been projected to that point on the screen. Yeah. How do we do it? Well, look at the diagram 7.5. So this point here is the one I've selected. We think of the projector line. So the projector line is the point, is the line emanating out of the viewpoint, emanating out of the origin, which goes through that point on the screen. So we're going to carry that line, imagine that line continuing into the world space, and it's going to intersect the real line. And it's that intersection point we want to pick up. So it's kind of like a line intersection problem. So what's the equation of that projector line? The equation of the projector line, that's the line that's shown in that diagram. Now this is kind of simpler vector equation for this line. It's going through the origin, so there's no P to use. I'm just going to use the origin as the reference. The projector line is coming out of the origin. And it's just going through, it's basically just going through this point. So I can represent this as, I'll put, what have I used so far? I've used mu and alpha, so I'll use lambda. So it's just lambda times R1 prime. Okay. R1 prime is the position vector at the point on the projected line. So this is the projector line for that. Okay. The line that goes through the origin, I'm using the origin as the reference point, so I haven't written it down, so it's just a zero vector, plus lambda times this point. So the line going from the origin through that point R prime. Okay. Now this intersects the real line in the world space when, what do I mean, when it intersects that line, when this expression here agrees with this expression up here. So when R, which is equal to lambda times R prime, so I'll write in R prime, it's P1 prime plus alpha P2 prime minus P1 prime. I'm taking some lambda times that, so this is the projector line. And this is equal to the expression I had earlier for the vector equation of the real line in the space, which is P1 plus mu P2 minus P1. Remember, the mathematical problem I'm trying to solve here is given alpha, find u. That's the problem I'm trying to solve. And it's kind of confusing because suddenly I've got this extra parameter. Remember, P2 and P1, they're part of the set. P2 and P1 are known to us. We know which points we're talking about. But suddenly I've got the appearance of this other parameter lambda. So lambda is the parameter which moves you along the projector line. I'm not particularly interested in finding lambda. rephrase the problem as I want to find the location on the point in the real world, on the line in the real world. So I just want to find the parameter mu. So in some senses, I want to eliminate lambda if I can. So get rid of them. So we're thinking of this as a problem of given alpha, find mu. So ideally, the kind of solution we're looking for is mu equals some kind of equation, an expression, and the things appearing here, well, components of P1 or P2 and alpha are going to be the things appearing in this expression. It's just the kind of solution we want. Before you dive into these things, it's off, think ahead and when will you know, what kind of situation are you heading for? When will you know you've succeeded? When we have some expression for mu in terms of the P1, P2, or their components, P1x or x1, y1, x2, y2, etc., and the parameter alpha. So what we'll do is we'll look at the components. Remember, there are three components. This is a vector equation. This is an equation amongst vectors. So there's three components to that equation. An equation amongst the x coordinates, equation amongst the y coordinates, and equation amongst the z coordinates. And they're not really all the same kind of equation because one of the equations features, see the z coordinates of all these vectors here on the left-hand side, they're all equal to f. So the z coordinates are kind of special. The z coordinates of these points are lying on the projection plane, all of them. But the z coordinates of the vectors on the right-hand side, they could be anything. So we'll look at the components of this equation. And we'll focus on the z component first of all. The z component is kind of special. So if we look at Rz, the z component here, what I have on the left-hand side is lambda. Now, what's the z component of P1 prime? Z component of P1 prime is f, of course. And the z components of P2 prime and P1 prime, well, they're both f, because they're projected. They're living on the projection plane. So this is actually quite a simplified left-hand side. It's just lambda times f. The z coordinates on the right-hand side is general. So it's going to be z1 plus mu into z2 minus z1. Once again, I've changed the way I've got the z. Sorry. So this simplifies a bit into f lambda equals this. Now, this is certainly not the kind of solution we're looking at. I mean, I could turn this around and it would tell me what mu is in terms of lambda. But that's not the kind of solution I want. I want mu in terms of alpha. Now let's look at one of the other components. This is only 1/3 of this equation. The equation amongst three-dimensional vectors. So there's three components. There's three equations on the component level. This is one of them. If I look at one of the others, if I look at the x components, what do I see on the x component level? Well, on the left-hand side up here, I see lambda multiplying, this is x1. Yeah, it's the first coordinate of P1 prime, which is f times x1 over z1. And then plus alpha into P2 prime. So this is going to be f x2 over z2 minus f x1 over z1. So that's the first component of the left-hand side. And this must equal the first component of the right-hand side. First component of the right-hand side is a bit simpler, of course. It's just x1 plus u into x2 minus x1. However, you see, on the left-hand side, what I'm aiming for is mu in terms of alpha and the x's and the y's and the z's. maybe the F as well. F is part of the setup as well, isn't it? Because it's the location of the projection plane. But as a common factor on the left-hand side here, I've got lambda times F. Lambda times F, lambda times F, lambda times F. So lambda F is a common factor at the left-hand side, and my analysis of the Z components have given me a nice expression for lambda F in terms of mu and Z1 and Z2. So I'd much prefer to see mu in terms of Z1 and Z2 in this expression instead of lambda F. That will get me closer to the kind of solution we kind of want. So taking account of the Z components, then this will simplify to lambda F, which is Z1 plus mu Z2 minus Z1. That's the lambda F. And that's multiplying into x1 over z1 plus alpha into x2 over z2 minus x1 over z1. That's the left-hand side there, and the right-hand side is still as it was, x1 plus mu x2 minus. Is this my answer? Remember, the answer I was looking for was an equation for mu in terms of the data. P1 and P2, or their components, which is x1, y1, x1, y1, z1, x2, y2, z2. I've certainly got that here. I have the parameter alpha. The parameter alpha is there, and then look up the parameter mu. But really, I just need to take this equation and make u the subject to get my solution. So just make mu the subject. There's nothing preventing you from doing that. Mu multiplies stuff on both sides. Just gather all the mu's together. You'll get a load of stuff on the other side. Mu will be multiplying a factor, so you just divide both sides by that factor, and then you'll have your equation mu equals whatever. Okay. Now, how much? You don't want to see me doing lots of algebra. And indeed, why the hell should we do it when we've got our wonderful computers to do algebra for us? There's a lot that, it's quite a fairly complicated expression. So in the Blue Peter tradition, I prepared this earlier. I've done it in Sage, but you can do it in Sage, or you can certainly do the same thing in MATLAB. In Sage, the command to set up symbolic variables is var. In MATLAB, it's sims. You do the same thing. Set up all the variables you need. I need z1, z2, x1, x2. I need an alpha and a mu. I set them all up. I type in the equation. So equation 1, or equation variable, holds this equation. Remember, you type in equations. See, in the computer language, you do EQ equation equals. That assigns a value to equation. And when you want to represent the equal sign in an equation, you use double equals. Okay, then MATLAB knows or Sage knows I'm telling it about an equation. So you set up the equation. So this here is the equation we just wrote down in the notes. Except it's even starting to do some work on it. So even though I typed it in exactly how we have it in the notes, it's already swapped things around with multiplying by minus sign. So it's done something funny. But then I've just asked it to solve for mu. Very similar command in MATLAB to solve a symbolic equation. Tell it the variable you're solving for. So this is our final solution here. This is a very nice equation now for mu. And interestingly, it's lost any dependence on the x and y. Well, we'd already lost the dependence on the y coordinates because we'd only considered the x component of the equation. But that's enough. And actually, in the simplification, the x1 and x2 disappear. So the parameter mu, interestingly, only depends on the z coordinates. It only depends on the depths of the points in the environment. Remember, z is when you're looking at the perspective projection, the z-axis is disappearing into the screen, so to speak. It's the distance from the viewer in the viewing direction. So the relationship of the parameter mu, which is the parameter along the line in the real world, to the parameter alpha, which is the parameter along the line in the projected world, well, there's a relationship for mu in terms of alpha, but the coefficients of it, the dependence on alpha is just governed by the z1 and z2 coordinates. So just the different depths of the two endpoints of the line. Okay? It doesn't depend on the x and y coordinates of the lines, just the depths of the lines. So that's good. So let me get this solution on the page. This gives mu. So it's I think doing it by hand would be kind of awkward, and you know, something I'd easily mess up on a Thursday afternoon. But this, really we should kind of work like this with computers now. You just look at that thing and you see, yeah, you can probably make mu the subject of that equation. There's nothing stopping you making mu the subject of that equation. And it turns out in the wash, the x and 1, the dependence on x1 and x2 disappears in the wash. So that's good. So this is our solution. This is our solution to this back projection problem. Okay. Remember, your mouse inputs with the computer, you move some selector around the screen, and you give the computer the parameter alpha. That's all the computer can extract from your action. So you're just selecting a point on the screen. But this is how, through the perspective projection, we can recover this parameter mu. And this parameter mu is the parameter along the line in the real world space. Okay. So this is our solution of this back projection. It's interesting that we can formulate it in such a way that it just depends on the two depths of the endpoints. And you could even divide above and below by Z2, say. You could divide above and below by Z2, and then you'd see it really only depends on the relative depths of the two endpoints. If you divide above and below by Z2, it'll just be alpha times that ratio, Z1 over Z2, divided by alpha times that ratio, Z1 over Z2, minus alpha minus 1. So the dependence is just on the relative depths of Z1 and Z2. So it's quite nice and pleasing solution. Okie doke. So that kind of completes chapter 7. So what I should do now is introduce the skeleton code for assignment 5. Was any questions about that problem first of all? Let me just okay. So let me sign back into this. Okay, let's have a look at assignment 5. So assignment 5 is titled Rendering a Virtual World. So what you have to do for this, the requirements are, you want to build a virtual environment out of some basic building objects. So some basic kind of house type objects, or you can get a bit inventive. If you can make complicated objects by just taking some time to map out the locations of the vertices originally, but then it shouldn't involve extra work in the code. Once you set these things up, the same code will take the same basic objects and perform all the steps. Now remember, you design your building objects in their own object space. So you specify your original object, you center it at the origin, and if it's got flat faces, line those up with the coordinate axes. Just to make it easy, I'm using a bit of pen and paper, map out the locations of the vertices of your basic building type object centered on the origin. Okay. And make its bottom positions be at the coordinate y coordinate 0. Remember, y is the vertical direction, so make its bottom coordinates be at level y equals 0, and then build it up in the positive y direction. So it'd be a typical building sitting on the ground. Okay. Then the code is going to produce, so then you'll have a bunch of objects in their own object spaces. The code is going to produce a world space, and you'll have to specify, you're going to use multiple copies of your basic building types and create a little village. So place the buildings in some kind of village arrangement. So arrange them on a plane clustered around a central point so as to produce a basic virtual world of a small village. Then we want you to produce a plan view of the village, as illustrated here. So this is just a view, an overhead view of the village. Now there's a function already in the skeleton code that will produce that. So once you set up the objects and once you do the transformations to put them into the world, your buildings will be in the world, and there's a function there that will draw this top-down view. Now here it's extremely simple. I've just got these two house shapes. So we're looking at the houses from above. Then you're going to use mouse clicks on this view to define a viewpoint. So there's going to be some viewing location and some viewing direction. That's the approximate location and direction that go together to form this perspective projected view. So this view on the right is what you want to end up with, a nice perspective projected view of your village. That's just the wireframe transparent buildings. But you can see there, obviously you can see you've got the perspective projection showing up there. Okay? So here we're viewing those two buildings from approximately this location, looking approximately in this direction. Okay? So the front face of this house is slightly to the left of our view, and the front face of this house is slightly to the right of our view. And you can see that that's how they appear. Now there's an additional requirement here to get some extra points, is to produce a street. A street is going to be choosing a direction in your village. Now I don't want you to laboriously, and I want 10 buildings down the side of each street. I don't want you to laboriously specify locations for each of these 20 buildings. I want you to use some kind of programming construct, what I've written there, use a suitable programming construct to iterate along the street, placing buildings to each side as it goes. So you can use the basic building types you constructed in step 1. You can use mouse clicks again or just build it into your code to specify some starting point for the street, some direction for the street, and have some programming construct. Think about what familiar programming construct will iterate along the street, will shoot out along the street, placing buildings to either side as it goes. Okay. Now, I don't ask you to do this from the ground up. I give you some skeleton code to do it with, which I'll show to you now. So this is up on Moodle beside the submission link. So you can download this code. So it's called Village Skeleton Code. It's multiple functions. So the top level function, this main function, which at the moment is called Village Skeleton Code, this is the program to run the whole process. This makes use of sub-functions, which are in the same M file but defined below this main script program. So this top function is the kind of program, the script to do all the actions, and it makes use, it calls the sub-functions. And the sub-functions are defined below, and makes use of built-in MATLAB commands and that. Now put loads of comments in the skeleton code so you can read through this. Well, I'll just take you quickly, just in the remaining time, just take you quickly through the code and point out some of the important aspects of it. So this is all comments explaining it. So the first actual commands are these commands here. And these define variables cube verts, cube poly, tetrahedron verts, tetrahedron poly. At the moment in the skeleton code, I've just got two basic building types, a cube and a tetrahedron. Okay? So cube verts will store the vertices of the cube. Cube poly will store the polygonal faces of the cube, represented as sequences of vertex labels. This is all explained in the comments. And similarly for tetrahedron. Now, I don't have the specifications there cluttering up my code. I've offloaded them into these functions. So I've written a function cube and a function tetrahedron. These are further down the code. So let's look at the function cube. Just scroll down to the function cube. Just show you cube. So they're pretty simple. So this is where you are going to design your basic building types. So here's my function cube. It has to return a set of vertices, a matrix of vertices and a matrix of polygons. It's explained what the feature should be. But if you look at it, it's not too hard. So here I've just specified in rows the vector using homogeneous coordinates, just the locations of the vertices of my cube. I've just thought of as a basic cube sitting at the origin. So these are the 8 vertices of the cube, the 8 corners of the cube. Specified their locations. I specified them in rows. It's easier to type it out and think of it in rows, and then I transpose it. Because remember, like we did in the previous assignment, we're storing locations of vertices as columns, pushing those columns together in a long matrix, and that stores all our vertices. And then I specify the polygonal faces of the cube. So the cube has 6 faces, so I've got 6 rows here. These are lists of vertex labels. So the first polygonal face is the face defined by the first, second, third, and fourth vertices. And then define the other 5 polygonal faces there as well. So that defines my basic cube type object. So you can look at that, and you can look at the other function tetrahedron, how I define the tetrahedron object. So you call these functions, and this gives you the vertices and polygon information for each of these objects. You then got a type vector, and here is where you specify how many buildings you're going to have. And here I've coded my 2 basic types. So I've got cube equals 1 and tetrahedron equals 2. If you've got more types, you'll have more different labels here. So you just have a label for each building that's going to be in your environment, and the label indicates which of the basic building types it's going to be. I then have a collection of position vectors. These are going to be the positions you're going to move your buildings to. I've got a collection of scale vectors. Again, this is all explained with comments. These are scaling factors in the x, y, and z directions for each of the buildings you're going to place. So you can have your basic building type, and you can stretch it. Scale it up, make it a big building, stretch it in one of the directions to make a different shaped building, and so on. And then also have a bunch of rotation angles. And these are going to be the orientations of each of your buildings. These are rotations around the y-axis. So you can take your basic building type and you can just change the way it's facing. We're not going to rotate it around the x or z-axis. That would tilt the building. You don't actually want to tilt your building, but you can rotate it around, change the direction it's facing. Then the code proceeds, and then you have a loop which runs through all your which runs through all your objects, runs through the number of buildings you're going to have. At the moment, they're in their own object spaces. You want to send them out into the actual positions they're going to be. So you have to translate each object. At the moment, this is just the identity matrix. It's still skeleton code. You translate each object, scale each object, and rotate each object. And you want to put those transformations together in the correct way to form a transformation matrix A. This transformation matrix A picks up your basic object type from its world space, sends it out, rescales it, rotates it, does those three operations in the correct order, which you have to agree and type in here, sends it out into the world space. Then the function, the skeleton code plots the world space for you. Okay, so there's a function I've written down below, plot world space, so that takes care of plotting the world space. I've even pre-programmed in all the stuff about getting the mouse clicks. So you're going to click on your plan view twice to give you a viewpoint and a direction of view vector. I'll show you how that's going to work. I'll actually run it. So I'll finish in a moment. Now, this code is not meeting the requirements yet. I've just got one cube and one tetrahedron. They're both plonked on top of each other, which isn't valid, at the origin. So that's not valid. But here you give so you click once. It's asking you to click to define the viewpoint. So I'm going to view it from over here. And my center of view, you then indicate a second point to indicate which direction you're looking at. I'll click over there. And it helpfully it draws the viewing vector on the world space. And then what should come up is the screen space, or the projected plane. Now at the moment, that is certainly not a perspective projection. At the moment, it doesn't do the perspective projection. That's just an orthogonal projection, straight. And it isn't even taking any reference of my viewpoint there. That's just orthogonal projection straight to the things. You see the cube and the tetrahedron superimposed on each other. But when you have the perspective projection programmed in correctly, what will come up there is the nice perspective projection, as an example of is shown in the assignment question itself. Now, the comments in the code point out all the locations where you have to go in and make changes. So there's all this code which grabs the mouse clicks, so that stays more or less the same. Then you come to aligning the world space with the direction of view vector. Now all the commands are there, but they're not the right commands at the moment. You'll need a certain translation to drag the viewpoint to the origin. You'll need a rotation around the x-axis and a rotation around the y-axis in order to align the environment. Those commands are kind of sitting there ready to work. The angles for them are just set at 0 at the moment, so you're going to have to go in and choose the right angles for those from the information in the mouse clicks. So you put those transformation matrices together in this overall transformation A, and this is where the alignment happens. You rename all the vertices as the matrix A multiplied by the vertices. That's where the alignment transformation is being carried out. And then you come to the place where the perspective projection is going to be carried out. The program determines an F value for you is just halfway between you and the nearest vertex in the world. So you can leave that as it is. Here I set all the Z coordinates equal to F, as they should be. Well, I've just left the X and Y coordinates unchanged. So setting every Z coordinate to F and keeping the original X and Y coordinates, that's just the orthogonal projection. Just ignoring the Z coordinate and just using the existing X and Y coordinates. So at the moment, all the code is carrying out is the orthogonal projection. You'll have to change these lines to make it do perspective projection. But you've got the formulas that we've looked at today. Just need to implement those into MATLAB terms. So once you've done that, the rest is taken care of. This function plot screen space, which I've written here, that's going to give you that final perspective projection view of your environment. And that's then where the main script ends. So the two plotting functions, to plot the top view and the perspective view, you won't need to go and change those probably. But then there's other functions at the bottom which you will have to change. You've already changed it. You've already done them in the two-dimensional sense with the wallpaper assignment. So there are functions at the bottom for a rotation matrix around the x-axis. That should return the 4x4 homogeneous coordinate rotation matrix for going around the x-axis by a certain angle theta. At the moment, it just returns the 4x4 identity matrix. Okay, but it should return the correct rotation matrix. You'd have to figure that out. It's just implementing the formulas from the notes. Rotation matrix around the y-axis. We don't ever use rotation matrix around the z-axis in this setup, so we haven't got it there. And then finally there's the translation matrix, which at the moment is just returning the identity matrix, but you'll have to replace that with its correct definition. So those sub-functions are called up in the main script program. So you want to write the general versions of them down here, and then you call the rotation matrices by angle, you call the translation matrix by x, y, and z components in your actual function. Okay, so that's a quick trip through the skeleton code. Just pointing out some things to you, but there's plenty of comments in there in the code, and John can help you with queries about it as well. And I've more or less highlighted in the comments all the places where you need to go in and fix it up to make it actually carry out the requirements there in the assignment as well. Okay, so we better leave it there for this afternoon. Gone a few minutes over. Sorry about that. I'll see you all soon.